And welcome to the week 14 Math 2414 review. In this one, we're kind of finishing up like our generic series. We're starting kind of what the next step is. So we're finishing up a lot of our basic series convergence tests, and we'll talk briefly about what a power series is. So first off, let's kind of just review a lot of our methods for determining whether or not a series converges or diverges. So when you are presented with a series, what's the first test you like to apply?
Divergence test.
Exactly. So first off, we basically always want to apply the divergence test because it's really easy, right? So if we apply the divergence test, then either we get that it diverges or we get that it's inconclusive, right? So if it's inconclusive, well, the next thing you usually want to do is going to kind of depend on a few different things, right? What your series is going to look like. So let's just talk about a few different things that could possibly happen. So let's say if it has factorials, or even if it has factorials, what do you like to do? I would say that with the factorials, you want to either do a ratio test, because the ratio test is usually pretty easy. What if it has powers of n?
Possibly do the geometric series
Right, so there are actually a few different cases where we might need to use, where that things might have powers of n. It could just be a geometric series. We could also potentially use the root test, right? And we can actually use the ratio test as well. So these are all valid possibilities. In fact, the ratio test is actually kind of like a more general form of your geometric series test. So basically, if it has a power of n in it, you could almost always apply the ratio test. In some cases, the root test might be a little easier, but the ratio test and the root test are pretty much going to get you the same result regardless. Okay, what if our series is alternating? Yep, this one's an easy one. We just kind of want to go with the alternating series test. Okay, what if we have like some extra fluff in there? So has coefficients or lower terms.
We can derive it maybe, or use the integral test. Oh, lower terms.
So like if we had like, for example, something like n squared plus 2n plus 5 over n to the 4th plus 3n squared minus 1.
Comparison test.
Which comparison test? Right, so the limit comparison test is really good at getting rid of things like coefficients, some lower terms, a lot of these extra fluffy things that don't really affect whether your series converges or diverges. And in this case, we would want to compare this one to just 1 over n squared, right?
Mm-hmm.
Biggest term on top is n squared, biggest on bottom is n to the 4th, n squared over n to the 4th is 1 over n squared. Okay, now if none of these things work, then we kind of want to get to some of our more difficult, maybe a little less savory tests. And those ones are usually, like you mentioned earlier, our direct comparison test, which is really useful and strong, but it can often be a little difficult to come up with a single good inequality to say, well, this series is definitely bigger than this one. And our other one is also the integral test, because a lot of the times integrals can be pretty hard to do, right? So sometimes the integral test is fantastic and it works great, but it's really hard to integrate certain things like, well, it's hard to integrate things that have a power of n. It's hard to integrate things that have factorials. It's really hard to integrate things that are alternating, things like that. So the integral test can be really powerful, but it can also be hard, so that's maybe why we kind of want to try it a little later. And one thing that I'm lastly going to note is keep an eye out for telescoping series, because sometimes those will crop up.
And those are the ones where we do the add, subtract, and plus up.
Yeah, that's where your terms are going to cancel with the later ones. All right. So let's go ahead and do a quick example. So let's say I had the sum from n equals 1 to infinity of n squared minus 1 over n cubed plus 1. Well, first off, I usually want to apply my divergence test, right? So I take the limit as n goes to infinity, and what is that limit?
That is infinity.
Well, it is infinity over infinity, but after I do, all my L'Hopital simplification, my limit is not 1. It's an n squared over an n cubed.
Oh.
Sorry. So my biggest term is on the denominator, right?
Yeah, so that's.
Let's really quick just go over the limit. So we're taking the limit as n approaches infinity of n squared minus 1 over n cubed plus 1. I could apply L'Hopital's, which would get me 2n over 3n squared, which is 2 over 3n. And then the limit as n goes to infinity of this is 1, or is 2 over infinity, so 0, right? Okay, so my divergence test tells me what?
That this does not diverge.
It doesn't even tell me that. It just tells me nothing, right?
Yeah.
It is inconclusive. So I applied my divergence test. It told me nothing. What do I do next?
And we can look at the other options, which this is a factorial, so it could do the ratio test.
Is it a factorial?
Or, not factorial, I lied. It has coefficients.
Okay, so, right, but it doesn't have like n as a power, right? So when I say it has powers of n, what I mean is like something to the nth power. So it doesn't have like powers of n. It has n's with some powers. Is it alternating?
No, it is not.
No. Does it have like some kind of coefficients or some lower terms?
Yeah.
Right. It's got some -1, some +1. Those are lower terms. So let's see if we can come up with a good limit comparison test. What do I want to limit compare it to?
I would do 1 over n.
Right. And we can come up with that 1 over n by just looking at the biggest term on top and the biggest term on bottom. So n squared over n cubed, which is 1 over n. All right, let's apply the limit comparison test. Limit comparison test tells me we need to take the limit as n goes to infinity of n squared minus 1 over n cubed plus 1, all over 1 over n. And I can rewrite that as multiplying fractions, so n squared minus 1 over n cubed plus 1 times n over 1. And that's the limit as n approaches infinity of n cubed minus 1 over n cubed plus 1, which is the same as the limit as n approaches infinity of, in this case, we have infinity over infinity, so we can apply L'Hopital's. 3n squared over 3n squared, which is just 1, right? Yeah?
So when we multiplied the n value, why didn't we multiply it to 1?
That is a good point, in which case this is going to become 3n squared minus 1. Ah, great, now I have to apply L'Hopital's again, but it was a mistake, you are correct. So we apply L'Hopital's again, limit as n approaches infinity. This becomes 6n over 6n, which is still 1, but yes. Another option we could do is we could actually take this and write it as the limit as n approaches infinity of 1 minus 1 over n squared over 1 plus 1 over n cubed. So basically just dividing everything by an n cubed, or multiplying by 1 over n cubed over 1 over n cubed if you prefer. Regardless, this limit is still 1. All right, and importantly, this limit is non-zero and it is not infinite. So our limit comparison test works, and it tells us that 1 over n and n squared minus 1 over n cubed plus 1 either both converge or they both diverge. Now, does 1 over n converge or diverge?
Because it gives you 0.
Right, this one diverges. By which test?
By the, it could be p-series as well.
Right. By p-series test is the most common. So, because we limit compared it to this series, n squared minus 1 over n cubed plus 1, this one would diverge by limit comparison. And there we go. All right, are you ready for a whole lot of practice problems?
Yeah. Question.
Yep.
So whenever I do the 1 over n, sometimes I forget to do p-series, and I plug in like infinity to that, and like it gives me 0.
Right.
Is there any way to still work with that? Like, if it equals to 0, then is there any rule that says that that's now convergence?
Well, remember your divergence test says that if your limit is equal to 0, then your divergence test tells you nothing, right? So some series have a limit that's equal to 0 of the terms, but they diverge, right? So if your divergence test fails, then you have to rely on some other tests.
Okay.
So if you don't want to use your p-series test, well, we could look at 1 over n and use the integral test, because the integral of 1 over x is the natural log of x, and that diverges as x goes to infinity, right? So the p-series test is really just like a specific instance of the integral test. I think I actually did that a couple weeks ago. Yeah. So for p is positive, then we can actually apply the integral test. And we see that we actually get an infinite integral when p is smaller than 1. But when p is larger than 1, we get an actual number. So because the integral would converge, then our series would converge when p is larger than 1. But yeah, that's just the integral test. You ready to move on? Perfect. Alrighty. Go ahead and just determine convergence and divergence. Whether it converges or diverges. And make sure you name which series tests you used. And I'll give you a few minutes to work through these 3. How are you doing? You get them done?
2 and 3.
Which one did you not get? You didn't get the first one?
No, I got tripped up by the coefficient of n.
So the fact that it was sine of 2n rather than just sine of n?
Yeah. Well, no, the sine of 2n, I kind of understood, like, because it goes between -1 and 1, and you can kind of make that 1, and then you can divide the 1 part by 1/2n.
Like this, you're saying?
Yeah, and then that's also less than 1/2n.
Okay.
But then when it gets to that 1/2n part, I wanted to do the divergence test, but because that would equal, or could I have done geometric?
Yeah, you could have done like a comparison to a geometric series because this series is strictly smaller than just 1/2n, right?
Yeah. When I say it out, I realize it.
Mm-hmm. And this one's a geometric series, so it converges. So then this one converges as well. And since this one is just negative this one, then this one should converge as well, right?
Mm-hmm.
Which means that the one in the middle must converge, right? Hooray! All right, what did you do for the second one?
So for the second one, I used the comparison test with p-series. By first, I wanted to compare it to like something similar to it, and I knew that like because the denominator, you keep adding things to it, you will find something that's greater by finding something that's the denominator is smaller. So I compared it to 1/n. That might have been jumping various steps.
Okay, so you're saying n plus n cosine squared of n is bigger than 1/n? I would agree with that. And then this is just, or sorry, bigger than, right?
Yes.
But then I would actually disagree with that. Because we have a larger denominator, right?
Mm-hmm.
So you have a larger denominator, which means a smaller number overall.
I can see that. That was nice.
Right. So we can't just do a direct comparison to 1/n. But I know that my cosine squared ranges between 0 and 1, right? Which means if I have this statement is true, right?
Yes, it is.
Which means 0 is less than or equal to n cosine squared, n which is less than or equal to n, right?
Mm-hmm.
Which means n is less than or equal to n plus n cosine squared of n is less than or equal to 2n if I just add n to everything, right?
Okay.
And when I take the reciprocal of all this, then all of my signs are going to flip, right? So rather than writing all of my signs as flipped, I'm just going to swap the order. So now I have 1/2n is smaller, 1/n is larger, right?
Mm-hmm.
Well, I know that this is smaller than this. So I have the sum from 1 to infinity of 1/2n would be smaller than the sum from 1 to infinity of 1/n plus n cosine squared, right?
Yeah.
Well, does 1/2n converge or diverge?
It diverges.
Right, we can just write it as 1/2 times the sum of 1/n. And this one diverges by p-series. So our overall series would diverge, specifically by direct comparison. By direct comparison, to 1 over 2n.
I believe there's a question like this on the quiz.
Ah.
Because I went directly to the
Yeah. Remember, we need to show that the smaller series diverges in order to show that the bigger one also diverges.
So whenever we do for direct, usually we try to go for the bigger one because if it's bigger, then what's inside of it would be equally as like divergent or convergent. But whenever we choose to find things that are smaller, is that like with the mentality that like double that will also?
So we choose things that are big or small based on kind of whether or not we think that the series converges or diverges.
Okay.
So if this, let's say that this side of the table is infinity and this side is 0. Sound good?
Yeah.
Well, I know that this series diverges, and I'm trying to figure out that this series, whether or not this series converges or diverges. If this series is smaller and it diverges, then the bigger one should diverge as well, right? It gets pushed by the larger one. So if we have one series and we suspect that it's divergent, we need to look for a smaller series that also diverges, because it'll push the bigger one to infinity.
Okay.
If we suspect that our unknown series then is convergent, we look for a bigger series because as it converges, it's going to push it to our real number.
Gotcha.
Yeah.
Okay, so diverge, if we try, well, if we did pass the divergence test, we would already know it diverges. But if we just have suspicions that it diverges, then we do the lesser than. And so for this one, your suspicions for it diverging, like, why did you choose that?
So I suspected that it diverged because I looked at the denominator and I saw that my largest term was an n. And I know that 1 over n diverges. So I'm saying this looks kind of like something that I know diverges. So since it looks kind of like it should diverge, I'm going to look for something smaller that diverges as well.
Gotcha. And we can't just keep it as, I see that one side of it, or a part of it diverges. We also have to be fully.
Yeah, so basically after a certain point, we don't really care about this part because we know that this diverges as well, right?
Yeah.
So once we know that that diverges, it doesn't really tell us about anything smaller, right? It just tells us that this is smaller than or equal to infinity, right? Doesn't really tell us a whole lot. But the fact that the smaller one must be equal to infinity tells us that the bigger thing has to also be infinity. Sound good?
Sounds good.
Okay, this third one, what did you do?
So for this one, I decided to use the series in certain ways as well as absolute convergence and ultimate.
Okay, and what did you conclude?
I concluded that it converges. It absolutely converges.
Absolutely. All right.
Conditionally.
I'm going to go with this one, conditionally converges. So we'll start with our alternating series test. And our alternating series test has 2 parts to it, right? First off, the limit has to go to 0. So let's take the limit as it approaches infinity of, well, we always consider the absolute value. So we have 1 over square root of n plus 4. The top is 1. The denominator goes to infinity. So this is 1 over infinity, which is 0, right? So that's our first condition of our alternating series. It also happens to pass the divergence test. So, or in other words, the divergence test fails. The next condition of our alternating series test is what?
I believe that's the like an over bn, or bn is.
You might be getting it confused with like the limit comparison test, or possibly, yeah. The second condition of our alternating series test is that our terms get smaller. So one way we can represent that is our n plus 1th term has to be smaller than our nth term. Sound good?
Yes. Okay.
Well, we can show this because we can say, well, 1 over the square root of n plus 1 plus 4 is smaller than the square root of 1 over square root n plus 4. Well, this isn't exactly immediately clear, right? But if we can maybe reduce it down into something that is immediately clear, well, this is true. So then we're just going to do some algebra. I'm going to cross multiply, so I have square root of n plus 4 is smaller than square root of n plus 1 plus 4, which tells me that the square root of n is smaller than the square root of n plus 1. And if I square both sides, then I have n is smaller than n plus 1, so 0 is less than 1. And this is, of course, true, right?
Yeah.
So because this is so trivially true, well, all I did was algebra to get back to this spot. So that tells me that my n plus 1th term is smaller than my nth term, and the second condition of my alternating series test is satisfied. Right? Which means that my series converges by the alternating series test. And you were wondering, well, does it converge conditionally or absolutely? And you said what?
After much consideration, I said absolutely. Initially.
Okay, you said it converges absolutely initially. And how did you make that conclusion?
Based on incorrect math where I used the absolute value bars to show that it converged when it was absolute.
Okay, but now you're thinking that maybe it converges conditionally, right? And how can we show that it converges conditionally?
By showing that sometimes it doesn't converge.
So remember, to determine whether it converges absolutely or conditionally, we look at the absolute value of the series. So we take the absolute value of the series, we get that our alternating part, the negative 1 to the n, just kind of goes away. So we're left with the square root of n plus 4. Right? Okay. Well, we need to show whether or not this converges or not. To do that, what should we do?
Well, we can simplify that or compare it to 1 over square root of n and then use the p-series test.
All right. So let's go ahead and use the limit comparison test to 1 over n. Or sorry, 1 over square root n. We apply the limit comparison test. We take the limit as n approaches infinity of 1 over square root n plus 4. I'm just going to go ahead and multiply by the reciprocal. Sound good?
Okay.
This is square root of n over square root of n plus 4, which is equal to the limit as n approaches infinity. This time, I'm just going to divide everything, or sorry, multiply by 1 over root n over 1 over root n. So 1 over 1 plus 4 divided by the square root of n. I plug in infinity. I have 1 over 1 plus 0, which is 1. And importantly, the 1 is not 0, and it is not infinity. So my limit comparison test is satisfied. And that tells me that either both 1 over square root n and 1 over square root n plus 4, they either both converge or they both diverge. Since 1 over square root of n, does this converge or diverge?
That diverges.
Diverges by which test?
By p-series.
So what can we say about the sum from 1 to infinity of square root of n plus 4?
Therefore, it diverges.
It diverges as well by the limit comparison. So then our original sum from 1 to infinity of negative 1 to n over square root of n plus 4, this one is going to converge only conditionally, right? Because it passes the alternating series test, but the absolute value of it does not converge. Sound good?
It does.
All right. Ready to move on?
1 second. So the reason why it converges conditionally is because though it passes the comparison test. Why did we say, I'm sorry, why did we say that?
So we know that this series converges
Mhm.
by the alternating series test, right?
Yeah.
But we can say that something converges absolutely if and only if the absolute value of it converges. So we take the absolute value of this series and we end up with this series. And this series, we applied the limit comparison test to this, right? And we got that our limit was 1, so either, which means that whatever this series does, if it converges, this one's also going to converge. If this one diverges, this one's going to diverge. So because this series diverges, this series needs to also diverge because it passed the limit comparison test. The limit comparison test doesn't always tell us that a series will converge or that it will diverge. It tells us that two series either both converge or they both diverge. They share the same convergence.
Okay.
So does that kind of answer your question a little? You still look a little lost.
Not fully there, because maybe I'm not understanding where the convergence conditioning part comes. Because I would have thought that since it that part diverges, then both parts will diverge, and I'll say diverges.
Right. So we can say that this series diverges, the absolute value version, right? Well, we know that our original alternating version converged by the alternating series test, right? So conditional convergence is specific to alternating series. If we have an alternating series and it converges by the alternating series test, but the absolute value of that series does not converge, that is the situation we call being conditionally convergent. It means that it has to be alternating in order to converge. So that's the condition.
Okay.
Yeah. If it converged regardless of whether or not it was alternating, then we'd call it absolutely convergent. Good? Well, let's go ahead and move on.
Yeah.
And talk about some geometric series. So let's take a look at a pretty nice series. Sum from 0 to infinity of x to the n. Now, this one looks a little different because I threw in x, which is a variable. But I could go ahead and start writing out terms, right? If I plug in 0, I get 1 for n. I plug in n is 1, I get x. N is 2, I get x squared. Then I have x cubed, and so on, right?
Yeah.
Okay. But I also know that this is actually a geometric series, right? So what's the ratio? Right. So it's a geometric series, and the ratio is x. Which means what terms or what values of x does this series converge for? Well, not quite. What does a ratio of a geometric series have to be in order for it to converge?
In order to converge, it has to be less than.
Right. So that means that the absolute value of my ratio has to be smaller than 1. Which means my x value can be between -1 and +1, right?
Yeah.
Cool. In fact, I can even find the sum for this ratio, right? My sum, whenever I have x between -1 and +1, I can say that my sum is my first term divided by 1 minus my ratio. Well, my first term is 1, right? And my ratio is x, right? Which means for whenever x is between -1 and +1, which is, I'm writing it like this, it's the same thing as this, I can actually make a function which is 1 over 1 minus x, and I can represent it using this power series. Pretty cool, huh? So you might be wondering, well, this looks a whole lot easier to work with than this, right? So what's the advantage of writing things as a nice big series, right? Because if we start out with this, sometimes we can go back and find this form. But what actually ends up being the case is a lot of the times it's really useful to start with a function and turn it into a power series. And the big advantage of that is this is just a polynomial, which means it just has constants and integer powers of x. And that is really nice because polynomials are pretty easy to work with. Whereas once we start getting more complicated functions, those can be a little less easy to work with. Anyway, this is called a power series. You'll notice that one of the restrictions we have is that our x value has to be within a certain small little area. And we call this the interval of convergence. And we also have a special word for this value here. We call this the radius. The radius is always equal to 1/2 the width of the interval. But you can also just think of it as, well, if I apply the ratio test, well, then I'm going to get, actually, let's just go ahead and apply the ratio test. I'm going to take the limit as n approaches infinity of my n plus 1 term over my nth term, right? This is x to the n times x over x to the n. Cancel my x to the n's. Well, then this x is completely independent of n, so I get x. Well, my ratio test tells me that this absolute value needs to be less than 1 for it to converge. I can think about this as being my radius of convergence whenever the interval, or sorry, whenever the coefficient on my x is 1. And you can think about it as if I sketched out what this interval was on a number line. Here's 0, here's -1, here's +1. Well, if I plug in x is equal to 0, then I get all zeros, right? So wherever I get all zeros as all the terms, I call that kind of my center of my series. So that occurs right here. And you'll notice that from the center of my series out to the edge of the interval, that's exactly my radius of 1. So let's do a slightly more complicated example. Let's say we have -3 to the n, x to the n, divided by square root of n plus 1. And I want to find the radius and interval of convergence. Well, whenever I'm looking to find my radius of convergence, I always want to apply my ratio test. So I'm going to apply the ratio test, which means I take the limit as n approaches infinity of a sub n plus 1 divided by a sub n. Now, I'm going to have -3 to the n plus 1, which I'm actually going to go ahead and write as -3 times -3 to the n, and have x to the n plus 1. So I'm going to write that as x times x to the n, all over square root of n plus 2. And then I'm just going to go ahead and multiply by the reciprocal as well. So that's the same as dividing by my a sub n. I'm just multiplying by the flipped version of it. We good so far? All right, time to start canceling things. I have a -3 to the n on top and bottom. I have an x to the n on top and bottom, which means now I'm left with the limit as n approaches infinity of -3x square root of n plus 1 over square root of n plus 2. Well, my x is completely independent of my limit. So I'm going to pull out an absolute value of negative 3x, which is just 3x, times the limit as n approaches infinity of square root of n plus 1 over square root of n plus 2. This limit comes out to be 1, so I'm left with 3x, technically still the absolute value, and this should be smaller than 1, right? Well, if I divide both sides by 3, I get that x, the absolute value of x, is smaller than 1/3. So what's my radius of convergence? Right. So I'm going to call this my radius of convergence. It's what I have when the coefficient on x is exactly equal to 1. So I found my radius. I can also see that my center of my series is going to be the point where all of my terms are zeros, right? So if I have a 0 for x, well, then that's just going to give me all zeros. So you look a little confused.
I think I got lost in the absolute value of square root of n plus 1 over square root of n plus 2. Did we just?
Yeah, I kind of did that limit really quickly. It comes out to being 1.
Okay.
Basically, the idea is the square root of n plus 1 and the square root of n plus 2, they're just off by a single like by 1, basically. And it's so little that as n gets very large, then it results in basically the same thing. I mean, we could multiply by like 1 over the square root of n all across, and then this would become square root of 1 plus like 1 over n, right? Over 1 plus 2 over n. But then both of these go to 0, and we're left with just 1, right?
Yeah.
Okay. But yes. So we get that our radius is equal to 1/3. We also know that our center is equal to 0 because when we plug in 0 for x, well then all of our terms become 0, right? Because we have 0 times whatever this value is. So our center is when x is equal to 0. And we have a radius of 1/3. Now, that tells me that the points where my series is going to converge are at least from 0 down to negative 1/3 and up to positive 1/3, right? But what if x was exactly equal to 1/3? Well, then I have that 3 times x, so 3 times 1/3 is equal to 1. What happens when my limit is equal to 1 for my ratio test?
Inconclusive.
It is inconclusive, which means I can say that whenever x is bigger than 1/3, it diverges. Whenever it's smaller than 1/3, it's going to converge as long as it's still bigger than negative 1/3. But when it's equal to 1/3, I actually don't know yet, right? So that's where I actually have to go through and come up with a different series test.
So you said when it's smaller than 1/3, it converges.
Right, so I said when x is, the absolute value of x is smaller than 1/3, then I get that by my ratio test, I get a limit that is smaller than 1, right? Which would then converge by my ratio test.
Okay.
When I have an x that's larger than 1/3, then I get that my 3x value is bigger than 1, so by my ratio test, it'll diverge. When I get that x is equal to 1/3, then 3x is equal to 1, and 1 is where my ratio test is inconclusive. Which means if I let x equal to 1/3, well then I now have the sum from n equals 0 to infinity of negative 3 to the n, 1/3 to the n, over square root n plus 1. Which is equal to, I can combine my negative 3 and my 1/3. So negative 3 times 1/3 is of course equal to negative 1. So I have negative 1 to the n over square root of n plus 1. Do we know if this series converges or diverges? Ooh, but it's an alternating series.
Yeah, conditionally convergent.
Right, so it conditionally converges. In this case, though, all we care about is that this one converges. If you wanted to check, you could use the alternating series test. Okay, what about when x is equal to negative 1/3? Because that's the same situation, but on the other side, right? Well, then we have the sum from 0 to infinity of -3 to the n, negative 1/3 to the n, all over square root n plus 1. In this case, though, the -3 and negative 1/3 turn into 1, so 1 to the n is just 1. So now we have 1 over square root of n plus 1. Does this series converge or diverge? It does diverge. We don't have time to go through like a proper test for why it does. But yeah, we could limit compare it to 1 over square root n, which diverges by p-series. Which means that whenever x is equal to negative 1/3, we shouldn't include it in our domain or in our interval of convergence. Well, when x is equal to positive 1/3, we should include it in our interval of convergence. Then we can write out our interval of convergence as being negative 1/3 not included up to positive 1/3, which is included. Sound good? Okay. So we found our radius, which is 1/3, and our interval, which is negative 1/3 not included to positive 1/3, which is. And again, you want to rely on your ratio test first to find that interval and that radius. Ready for a practice problem?
Sure.
All right. So find the radius and interval of convergence of n factorial times x to the n. And after that, if you have time, do x to the n divided by n factorial. Everything's looking a little odd. Good. That means you're doing it right.
Okay. But when it's wrong.
How's it looking? All right.
Next question.
What?
Going on to the next question.
What did you get for the first one?
So the equation looked weird,
Uh-huh.
and I feel like there's too many n's.
Uh-huh. All right. So we apply the ratio test, right?
I did.
Okay. And that would be of that would basically be n plus 1 factorial, right?
Mhm.
Which is n plus 1 times n factorial times x to the n plus 1, so x times x to the n, all divided by n factorial times x to the n, right? Right?
Yeah, but I messed up one thing that might have been why everything looks wonky.
Okay. So from here we can cancel out n factorials and our x to the n's, right? So we're left with the limit as n approaches infinity of n plus 1 times x, right? And what is this limit? You're saying not infinity?
Is infinity?
It is infinity, right?
We bring out the x, right?
Yeah, we could. Is there one situation where it wouldn't be infinity? What could x be to make the limit not infinity? Well, I'm multiplying by x, right?
Can you restate the question?
Yeah, sure. So I'm wondering, is there a value of x that will make my limit not infinity? And you said?
0.
0, right. So this limit is equal to two things depending on the value of x, right? It's equal to 0 if x is equal to 0, and it's equal to infinity if x is not equal to 0, right? Well, when does my series converge? Only if my limit is less than 1, right? Which means that my series only converges when x is equal to what? I would say it only converges when x is equal to 0. Because whenever my x is not equal to 0, well, my limit is infinite, right? And because infinity is larger than 1, by my ratio test, it would diverge. So my limit has to be smaller than 1 in order for my series to converge, and that only happens when x is equal to 0. Does that make sense?
So let's run that one more time. So the series only converges when it's less than 1, or usually that's the test of convergence.
Right.
And then, so when x is not equal to 0, it goes infinitely. So then would we then gauge it as infinity is? Oh, okay.
Is infinity bigger than 1?
Yeah.
Yeah. So then we'd say that it diverges.
I see.
Yeah. But when x is equal to 0, then we just have the limit as n goes to infinity of 0, which is still 0, right?
Yeah.
Yeah. So that's really the idea. So because we only converge at a single point, well, then the radius is actually equal to 0. And the interval, well, it isn't really an interval at all. It's actually just a single point, 0, which we could write as x equals 0. Now the second one looks kind of similar. I'm just going to go over, we're running a little short on time, so I'm going to jump right into it. So we have the limit as n approaches infinity. Again, we're applying the ratio test first. This is going to be x to the n plus 1 divided by n plus 1 factorial times the reciprocal, so n factorial over x to the n, which is equal to the limit as n approaches infinity of x times x to the n over n plus 1 times n factorial times n factorial over x to the n. What cancels? Well, my x to the n's and my n factorials, so I'm left with the limit as n approaches infinity of x divided by n plus 1, right? Now I'm going to go ahead and pull out my x since it's independent. And I'm left with the limit as n goes to infinity of 1 over n plus 1. And what is this limit equal to?
This is equal to 0.
And is 0 larger than or smaller than 1?
It's less than 1.
Right. So what x values will my series converge for?
It'll converge when it's greater than 0.
Well, I could also have it smaller than 0, right? Because no matter what, my limit's going to end up being 0, right? So in this case, I can actually say that my radius is infinite. Because I can have as big of an x value as I want, and this limit is still going to go to 0, right? And that's still going to be smaller than 1. There is no way I can use my ratio test to get a number larger than 1 so that my series is going to diverge. So my radius is infinity, which means that my interval would be all real numbers. Make sense? So there's basically 3 cases that can happen when we have a power series. We can either have that it converges at a single point, the center, and that's what we saw here. We can have that it converges for all real numbers, and it'll have an infinite radius, which we saw here. Or we can see that it's got something in between. So it converges for some interval that's bigger than just a single point, but it's not all real numbers. And that's what we saw in the example of here. Sound good?
And you said this is the power series.
These are called power series. And power series, all they are is they're just basically an infinite polynomial. So like a0 plus a1x plus a2x squared, and so on. Just something that looks like that. You could also see them shifted a little bit. So like b1 plus b2 x minus c plus, and so on, something like that. Where all we're doing is we're just moving where the interval is. But yep, that's called a power series. Anyway, we're about out of time for today, so thanks for coming, and have a good one.